For decades, we have gazed at the red dust of Mars, quietly searching for signs of distant life. But perhaps we have been looking in the wrong place. Almost 400 million miles away, a world wrapped in ice holds a profound secret. A vast, hidden ocean with an estimated twice the amount of water as all of Earth's seas combined. We've suspected it was there for some time. But new evidence has gently shifted our perspective. What scientists are finding under the ice points to a world that is far more active and far more mysterious than we ever imagined. Tonight, we'll drift into the story of what they found under Europa's ice dot in our solar system. Jupiter is a silent king. It's a vast world of gas and tranquil storm, so large you could fit all the other planets inside it. But circling this gentle giant are its moons, and one of them, a small, quiet world named Europa, has slowly become one of the most compelling destinations in our entire solar system. From a distance, Europa doesn't seem like much. It's about the size of our own moon, a pale sphere, crisscrossed with a delicate network of dark reddish-brown lines. When the Voyager spacecraft drifted past in the 1970s, the pictures it sent back showed a world that was beautifully strange. Our moon is a fossil, covered in craters from a distant, violent past. The same is true for Mercury and many of Jupiter's other moons, like Callisto. Their surfaces are history books, written in scars. But Europa was smooth, serenely smooth. In fact, it's the smoothest known object in the solar system. Where were all the craters from billions of years of cosmic impacts? Their absence could only mean one thing. Europa's surface was young, perhaps only 40 to 90 million years old. Something was gently wiping the slate clean, erasing its history. This realization was a quiet turning point. Europa wasn't a dead, frozen rock. It was geologically active. But what could be powerful enough to resurface an entire world? The answer, when it was proposed, was elegant. A vast, global ocean of liquid water, hidden beneath a shell of solid ice. The idea was that the ice shell was not a static block. It was a dynamic crust, floating and shifting on a liquid ocean below. Cracks would form, water would well up and freeze, creating a new surface, while old ice was pushed back down. That smoothness wasn't a sign of stillness. It was the ultimate sign of quiet activity. This was the birth of the Europa ocean world theory. The idea that just beneath that frozen surface lay more liquid water than on our entire planet. It was a wondrous thought, but for a long time, it remained just a theory. Scientists were like detectives at a cosmic puzzle with plenty of clues, but no final piece. They needed more hints to suggest the ocean was real, and that evidence would come from a mission that would change how we see the outer solar system forever. Every great story of discovery has its moment of quiet revelation. For Europa, it came in the late 1990s, thanks to a spacecraft named Galileo. Galileo was on a grand tour of Jupiter and its moons. One of its tools was a magnetometer, an instrument that measures magnetic fields. Jupiter has the most powerful magnetic field of any planet, a vast environment that swirls around it for millions of miles. As Galileo flew past Europa again and again, its magnetometer detected something unusual. The magnetic field around Europa wasn't just Jupiter's. There was a second magnetic field, a much weaker one, being generated from inside Europa itself. This is not typical for a moon. A small, icy body like Europa shouldn't have its own magnetic field. Its core would be too small and frozen to generate one as Earth does. So, what was happening? Scientists realized they were observing something called an induced magnetic field. It works on a simple principle. If you move a large magnet over something that conducts electricity, it creates a faint electrical current, which in turn generates its own faint magnetic field. Jupiter's powerful, rotating magnetic field was the giant magnet. The fact that Europa was creating its own secondary field meant there had to be something conductive inside it. Rock is not a great conductor. Ice is even worse. But you know what is? Salt water. This was a profound clue. The Galileo data only made sense if there was a massive globe-spanning layer of salty liquid water under the ice. The magnetic field wasn't just a hint. It was a measurement. It told scientists the ocean was real, it was global, and it was salty. The ocean was no longer just a hypothesis. It was a measured reality. With the ocean's existence now strongly supported, scientists looked at the surface with new eyes. Those strange lines and jumbled blocks of ice suddenly made more sense. They saw large areas called chaos terrain, and they looked just as they sound. A gentle disarray of ice blocks, tilted and drifted and frozen in new spots, like icebergs that broke from a glacier, floated for a while, and then were frozen in place. One of the largest is called terra regio. This kind of landscape is best explained by the ice shell slowly melting from below, causing the surface to collapse, shift, and then refreeze. It's a direct sign of a warm ocean interacting with the ice above. And then there were the long, reddish-brown cracks called linea, stretching for thousands of miles. Scientists now think these happen when the ice shell is stretched and pulled by Jupiter's immense gravity. As Europa orbits, it's constantly being squeezed and flexed. This tidal force creates great stress in the ice, cracking it open. Water and brines from the ocean below can then well up, freeze, and stain the surface with whatever minerals they carry. This led to another incredible possibility. If the ice is cracking, could water from the ocean actually escape into space? Astronomers searched for years, and then, using the Hubble Space Telescope, they found it. On multiple occasions, Hubble spotted the faint signature of water vapor erupting from Europa's southern hemisphere gentle, plumes reaching hundreds of miles into space. This was a remarkable finding. Not only was it more direct evidence for liquid water, but it meant nature might be providing a free sample. We might not need to drill through miles of ice. We could simply fly through the plumes and sense what is coming out. For years, the magnetic field, the chaos terrain, and the plumes were the foundation of our understanding. We knew an ocean was there, but we didn't know what it was like. Was it a sterile, empty place? Or was it something more? This brings us to the something they found. The new evidence that has transformed Europa from a world with a quiet, hidden ocean to a world that's chemically rich and active today. The first clue came from the most powerful space telescope ever built, the James Webb Space Telescope. JWST used its infrared vision to study Europa's surface chemistry and confirmed it was covered in carbon dioxide ice. But the key question was, where did it come from? Was it delivered by meteorites? Or created by radiation? JWST's data offered a wonderful answer. The carbon dioxide was most concentrated in terra regio, that same young, chaotic region where material from the ocean is believed to have recently surfaced. The conclusion: the carbon was not from an outside source. It came from the ocean itself. This is a truly significant finding. Carbon is the backbone of life as we know it. Finding that Europa's ocean is carbon-rich, and that this carbon is actively cycling to the surface, makes the world much more promising for habitability. The second piece of new evidence came from taking a closer look at those reddish-brown stains. For decades, scientists thought the ocean was probably full of magnesium sulfates, essentially Epsom salts. But newer, higher-resolution observations challenged this. They found that in certain areas, especially the chaos terrains, the signature didn't match magnesium sulfate. It matched something much more familiar: sodium chloride, table salt. When sodium chloride is exposed to radiation like it is on Europa's surface, it turns a yellowish-brown color, the exact color seen in those strange lines and chaos regions. This implies Europa's ocean might not be a bitter sulfate sea, but a chloride-rich ocean, chemically much more like our own. A salty sodium chloride ocean hints that processes like hydrothermal activity could be happening on Europa's seafloor. The final piece of the puzzle is a total rethinking of the ice shell itself. It's not just a lid that cracks. New models and a fresh look at old Galileo data strongly suggest Europa has a form of plate tectonics, but with plates of ice. Not rock. Scientists have found what look like spreading ridges, where the ice shell pulls apart and new ice forms, just like the mid-Atlantic ridge on Earth. Even more importantly, they found evidence for subduction zones areas, where one massive plate of ice slides under another, diving back down into the warmer interior. This idea of ice tectonics is a peaceful revelation for habitability. Here's why. Europa's surface is constantly bathed in radiation from Jupiter. This radiation creates powerful oxidants, like oxygen and hydrogen peroxide chemicals that can provide energy for life. The great puzzle was always how to get those chemicals from the surface down into the ocean. Subduction is the perfect delivery system. It's like a gentle planetary scale conveyor belt. Ice plates on the surface, full of chemical food from the radiation above, are slowly forced down, carrying those life-sustaining chemicals into the ocean below. So, when we say they found something, we're not talking about one single thing. We're talking about the discovery of a system. A system where a carbon-rich, saltwater ocean is chemically connected to its surface. A system where active ice tectonics could be dredging up material from below and carrying nourishment for life back down. We've gone from a static picture of an ocean under ice to a dynamic, quietly breathing world. And this new understanding leads us to the biggest question of all. If this world is so active and has all the right ingredients, what could be living in it? To truly grasp the possibility of life on Europa, we first need to go over the basic recipe for life because we know it. It gently boils down to three things. First, you need liquid water. Water is the universal solvent, the medium where the chemistry of life can unfold. Second, you need the essential chemical ingredients. Life on Earth is carbon-based and relies on elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Think of them as the building blocks. Third, you need a source of energy. Life is an active process. It needs energy to continue. On Earth, most of that energy comes from the sun. For decades, this recipe has guided our search. Now let's apply it to Europa with everything we've just learned. First, liquid water. Europa has this in abundance. It doesn't just have an ocean. It has an ocean with an estimated 2 to 3 times the volume of all of Earth's oceans combined. So, the first ingredient is there in overwhelming supply. Second, the chemical ingredients. This is where the new discoveries are so important. We suspected the chemicals were there, but now we have real evidence. The James Webb Space Telescope's discovery of carbon coming from the ocean confirms its sea is carbon-rich. And that ocean sits right on top of a rocky mantle, just like on Earth. For billions of years, water has been reacting with that rock, leaching minerals and nutrients like phosphorus and sulfur into the ocean. The discovery of sodium chloride strengthens the case for a mineral-rich sea. And the ice tectonics we talked about provide a way to deliver oxygen from the surface down into that ocean. So the building blocks appear to be there. That leaves the third and most critical ingredient: energy. Europa is nearly 400 million miles from the sun, where sunlight is about 25 times weaker than it is here. It's far too weak to power photosynthesis, and it certainly can't get through a 10 to minus 15 mile thick ice shell. For a long time, this was the biggest hurdle. No light, no life, it was thought. The answer isn't the sun, it's Jupiter. Europa is locked in a gravitational dance with the giant planet and its other large moons. This cosmic ballet forces Europa into a slightly elliptical orbit. As it gets closer to Jupiter, the gravitational pull is stronger. As it moves away, it's weaker. This constant flexing, a gentle stretching and squeezing, over and over again every 3.5 days, is called tidal heating. It generates a huge amount of energy inside Europa. A simple way to picture it is to take a paperclip and bend it back and forth. The metal at the bend gets warm. The energy from your motion has turned into heat. Now, imagine that happening to an entire world. This friction needs Europa's core and mantle, generating enormous heat from the inside out. This internal heat is the key. It's what keeps the ocean liquid in the first place. But it almost certainly does more. It could power volcanoes on the seafloor. On Earth, in the deepest, darkest parts of our oceans, we've found this exact thing. Along mid-ocean ridges, seawater seeps into cracks, gets superheated by magma, and returns as a plume of warm, mineral-rich water. These are called hydrothermal vents. When they were first discovered in 1977, they completely changed our understanding of biology. Here, in total darkness and under immense pressure, were entire ecosystems thriving, with no connection to the sun. The base of the food chain wasn't plants. It was bacteria using chemosynthesis. These microbes were consuming chemical energy, metabolizing compounds like hydrogen sulfide from the vents. An entire food web was built on them. Giant tube worms, pale white crabs, and translucent shrimp, all living in a world powered by the planet's own internal heat. This is the model for life on Europa. The tidal heating almost certainly creates a hot, rocky seafloor. It's overwhelmingly likely that Europa has its own hydrothermal vents, releasing heat and chemical nutrients into the dark ocean. The implications are profound. Europa doesn't just have one or two ingredients for life. It seems to have all three: liquid water, the right chemistry, and a powerful energy source that has nothing to do with the sun. So let's wonder. Imagine descending through that 15-mile thick ice shell. The pressure builds, the darkness is absolute and peaceful. And then you break through. You're floating in a black ocean. The ice ceiling is a distant, unseen surface above. Below you is the seafloor. In the distance, a faint warmth. As you get closer, you see them. Chimney-like structures, venting dark, warm plumes into the cold ocean. Europa's hydrothermal vents. And they aren't empty. The rocks around them are covered in thick mats of microbial life, the chemosynthesizers, the foundation of this ecosystem. European bacteria, harvesting energy from the planet's core. Crawling over these mats are more complex organisms, perhaps slow, slug-like grazers. Clinging to the vents are creatures filtering nutrients from the plume. Maybe there are small, shrimp-like scavengers, darting gently in and out of the warm water. Could there be predators? In an ecosystem like this, it's a logical next step. Not Hollywood sea monsters, but maybe something like a fish or a squid, perfectly adapted to a high-pressure, lightless world, a hunter with no eyes, but senses tuned to pressure and the faintest chemical trails in the water. This isn't just fantasy. It's a plausible guess based on the conditions we think exist on Europa and what we see in similar places on our own planet. The discovery that Europa is an active, dynamic world with a carbon-rich, salty ocean and a system of ice tectonics has turned this from a hopeful dream into a real scientific possibility. For the first time, we're looking at another world in our own solar system and finding not just the possibility of life, but a quiet expectation of it. And we are on the verge of finally getting some answers. For all our deductions and models, we are still on the outside looking in. The clues are compelling, but the ultimate question, is there life in Europa's ocean, remains hidden under miles of ice. To find out, we must go back. And that is exactly what we are doing. The next chapter in this story is a mission called Europa Clipper. Launched in October 2024, it is NASA's most advanced spacecraft ever sent to investigate an ocean world. Its journey is a long and patient one. After getting gravity assists from Mars and Earth, it will finally arrive in the Jupiter system in April 2030. Clipper will not orbit Europa directly. The radiation there is so intense, it would damage the spacecraft. Instead, it will make a series of graceful looping orbits around Jupiter, allowing it to perform 49 high-speed, low-altitude flybys of Europa, some as low as just 16 miles above the surface. During each pass, its 9 powerful instruments will map, scan, and sense the moon in incredible detail. Clipper's goal isn't to find life directly. Its mission is more fundamental: to determine if Europa is truly habitable. It is designed to answer the big questions and create a treasure map for a future mission that could search for life. So, what's in its toolkit? First, it has a powerful ice-penetrating radar called Reason. This will send radio waves through the ice shell to map its thickness, search for pockets of trapped water, and hopefully detect the top of the ocean itself. Next, its magnetometers will measure the ocean's depth and salinity with far greater precision than Galileo ever could. A suite of high-resolution cameras will map the surface in stunning detail, helping scientists understand the geology of the chaos terrains and ice tectonics. And a thermal imager will scan for warm spots areas where heat from the ocean might be escaping. Most wonderfully, Clipper can analyze the moon's chemistry from orbit. Spectrometers will map the surface to confirm the presence of sodium chloride and search for other organic molecules. And if Clipper is fortunate enough to fly through a water vapor plume, a mass spectrometer will be able to directly sense the material erupting from the ocean, tasting it for the chemical signatures of life. By the end of its mission, Europa Clipper will have given us a complete portrait of this ocean world. It will have mapped the ice, measured the ocean, and decoded the chemistry. It will pinpoint the X that marks the spot for the ultimate mission, a future lander. And the dream does not end with Clipper. Scientists are already designing the next step, a lander that would touch down on one of those promising sites to drill into the ice and sample materials shielded from the harsh radiation. Beyond that lies the quiet hope of robotic exploration. A cryobot, a nuclear-powered probe that would melt its way down through the entire ice shell, unspooling a fiber optic cable to stay in touch. And once it reaches the ocean, it would release a small, autonomous submarine to swim free in the dark, its lights searching for the warmth of a hydrothermal vent, and its cameras looking for the first evidence of extraterrestrial life. This may sound like science fiction, but it is the concrete, long-term goal. We started with blurry Voyager images of a strange, smooth world. Galileo gave us the proof of an ocean. Hubble and JWST have revealed the dynamic chemistry of that ocean. Now, Europa Clipper is on its way to give us the maps we need to finally go there. The search for life beyond Earth is one of the most profound quests we've ever undertaken. For so long, it's felt like we were gazing out into a silent, empty universe. But on a small moon orbiting a distant gas giant, we may have found our first real reason for hope. Europa appears to have the water, the chemistry, and the energy. It has all the ingredients. The ice has kept Europa's secrets for billions of years. But now, we're finally gently starting to crack it open. If you wish to dream of these worlds with us again, feel free to subscribe. The answers to one of humanity's oldest questions might be just a few years away, waiting to be whispered across the stars.